In this video we're going to look at the absolute basics of differential equations. But first of all, let's start off with something that's simpler than a differential equation. So let's imagine that we've been given a problem. We've got a graph here, okay, so that's the graph y equals x squared plus x minus 6, and we're asked to find the roots of that equation. Now, by the roots, what we mean is where the graph passes the x-axis. So that's x-axis there, the y-axis there. So we can see here that it passes that axis when x equals 2 and whenever x equals minus 3. Now, we're used to solving that there by using factorization, so we can write that as y equals x plus 3 times x minus 2. Okay, so we multiply these out, you get the equation above. Now we know that's correct because if whenever I click on that to draw that out, it should just draw it right on top of the graph we've already got. Okay, so that's done that, it's actually drawn it there. Okay, so it's the exact same equation. Okay, now we can find the roots of that by setting y equals 0. So then we end up with x plus 3 equals 0, so x will equal minus 3, that's one of the solutions, and x is going to equal 2. Okay, so that's us found the roots of that equation. Now we're used to seeing that, and we can see that this is an equation. There's got something on one side, there's an equal sign, something on another, and the solution to it is two numbers, minus 3 and excuse me, plus 2. Now we're going to get rid of that, and we're going to start looking at not an equation, simple equation there with a y at one side and a function at the other. We're interested now in equations with a y derivative in it. Okay, so let's imagine that we first of all we start off with a function y equals x squared. Okay, now if we were to look at the gradient of each of the points on that curve, then we could create this gradient here by just shifting, like that, we're shifting this value down along the curve. Okay, so that blue line there gives us the gradient at each point there that it's tangent to that curve. So for example, if I zoom in a little bit there, if I go to the point where x equals 1, okay, if I can bring it down there, okay, so x is equal to 1, okay, so y equals x squared, so it's 1 squared is equal to 1, so that's on the red curve. But the gradient of that there, well, we know from basic calculus that if y equals x squared, then when we differentiate y equals x squared, we get y equals 2x, so that's equal to the y equals 2x there. I'll just take that off just now. So it means that the gradient at that point is going to be given by this curve here. So the gradient at that point there, 1, is going to be 2 times 1, which is going to be equal to 2. So the gradient of this blue line should be 2. And you can see that it is 2 because we come down 2 and along 1. So that's y upon x is 2 upon 1, the gradient is 2. So if we went to, for example, the y x equals 2, okay, so that's a point where x equals 2. I'll put it, just write it exactly in, okay, 2, okay, so that's where x equals 2. So when x equals 2, then the gradient at that point there on the curve is going to equal 2 times 2, which is going to equal 4. So that blue line should have gradient 4, and you can see that it has got gradient 4. You come down 1, 2, 3, 4 and along 1, so the gradient of that is 4. Okay, so that just gives us all of the gradients at all of the points, and we can just draw out the graph of all the gradients, and that's that line there, y equals 2x. Now the reason for showing us that is we're going to use this example, y equals x squared and y equals 2x, in order to write out our first differential equation. So if I was to go and write this equation out, so if we were to have our first differential equation is the equation y derivative equals 2x, and we're told to find the function y of x that makes that true. Okay, so the way you're going to read this is that it's obvious from what's written here that we've got x as an independent variable, so x is along this axis, it's an independent variable, and our value y is up that axis, and it's our dependent variable. So a question of this type means that it'll have some sort of geometric meaning. Okay, so it means you could always draw it out and it'll have some sort of meaning geometrically. So we already know from what we did in the previous clip there that the solution to this thing here is, well, it's saying give me a function y of x such that whenever I whenever I differentiate that function, it's going to give me a value of 2x. So I'll say that again. It's the question is saying find a function y of x such that whenever you differentiate it, you get a value 2x. Okay, so we could really write that, and that really should say y derivative of x equals 2x, but generally they don't bother putting in that x there because it's understood that that y is a function of x. Okay, so I'll just rub that out there. It was just a little note there. Okay, so rub that out. So now we're kind of cheating because we already know the answer. Okay, so we know that the function that we have whenever we differentiate it gives us 2x. That function's got to be y equals x squared. Okay, so we know that's true because whenever we differentiate that we get 2x. So that's our solution. Our solution is y equals x squared. But we have to be careful here because that's not the only solution, because y equals x squared is not the only graph that has a gradient of 2x, and you can see that whenever we go back to our graphical calculator. Okay, so when you go back to that graphical calculator, I can actually put in f of x equals 2x plus, say, plus 1. Now that graph there also has the same gradient y equals 2x, because when I differentiate that, I get y equals 2x, the 1 will just disappear. Okay, so when I shift that round about, that will give us a gradient at every point, and the gradient will be given by 2 times the x value. So I could put in any value here, any constant. So I put in a constant c, and I can slide that graph up and down. Okay, so I slide that graph up and down, the gradient remains exactly the same. The gradient remains at that value. So for example, if I just shift, where's this one? So I shift that, put that to 1. Okay, then the gradient of that blue line is 2. Okay, but if I shift that up and down, the gradient still remains 2. Okay, so it doesn't matter where I move that round about. Whenever I shift this line up and down, the gradient always remains the same. So that means that there's not just one solution to this problem, there's actually a whole family of solutions. So every function of the form y equals x squared plus c is a solution. Okay, so that means that if we were to go back into our drawing package here, and let's see, so that means that not only is y equals x squared a solution, also y equals x squared plus a constant c is a solution. Now that there is called the general solution, so I won't write it all out, I'll just put GS because my writing's terrible. So that y equals x squared plus c is the general solution to that differential equation. So that's our first differential equation we've looked at and that we've solved. Okay. Now there is another extra part here, because if we were given a bit more information, so let's say we were told that we had to solve that for y of x, but we're also given one condition. We're told that whenever x equals 0, y equals 2. So that thing there is called an initial condition. Okay, so we'll just put that down here. We'll call it IC, so that's the initial condition. So the initial condition is y of 0 equals 2. Now be careful how you read that. What's that's saying is that when x equals 0, y equals 2. It's not saying y equals 2 and x equals 0. Okay, so when x equals 0, right, y equals 2. Okay, so let's put that in. Okay, and we can solve that. So you could go back here and look at it in, well, we'll solve it here first of all, actually. So we'll solve it here. So given that initial condition, we can find that value of c, that constant. So we can say that when y equals 2, okay, and x equals 0, so we put in 0 for x, so 0 squared is 0. That would mean that c must equal 2. So that would mean that the equation, the solution for that becomes y equals x squared plus 2. Okay, and that there is called the particular solution. I'll just write PS. Okay, so that is the particular solution. So that there is the final solution to our problem. Okay, so if the problem is written like that, the problem reads: find a function y of x such that y derivative of x equals 2x given the initial conditions y of 0 equals 2, and the solution to that is y equals x squared plus 2. So, and we can see that again back in the graphical calculator. Let me bring it up there. If I had a value of 2 in there, all we're doing with the initial condition is ensuring that we have one value on that curve. Now it could be any value in the curve. It doesn't need to be a value whenever x equals 0 and y equals 2. It could be x equals 1 and y equals 3. All we need is just one particular point on this curve. Okay, so it would mean that if we had one point on a curve, we would be able to pick out the exact curve that is the solution curve from the entire family of curves, okay, that you can see whenever you shift up and down. Okay, so that means that we're picking out, we're coming along here and we're saying, well, what curve is it that we're going to use? Okay, you say, well, the initial condition is that whenever x equals 0, y equals 2, and we say bang, okay, it's this curve here. Okay, so that there is the most basic and simple way of looking at an example of a differential equation. Now we'll look at one other. Let's see if we can bring up our smooth draw. There we go. So we'll look at one other example, okay, and we can see how this example kind of looks in a kind of graphical sense. Okay, so if we had the example as y derivative times y equals minus x, and we were to say, we were asked to show that x squared plus y squared equals 1 is a solution to this differential equation. So we can rewrite the left hand side as y derivative equals minus x upon y. Okay, so we're going to show that this here satisfies that. Okay, so what we have to do is we've got to differentiate this. Okay, so when we differentiate this, it's implicit differentiation. So we're going to be saying d of x squared, okay, by dx plus d of y squared dx, okay, equals d of 1 by dx. Now the first part here is going to be 2x, so you're going to have 2x. This thing here is implicit differentiation, so there's a video in my snippet section if you're unsure about implicit differentiation, so you can go and have a wee look at that. Okay, so that's going to be plus 2y times y derivative, and that's equal to the left hand side, that's going to equal 0. So then we can then rewrite that out, take the 2x across, so you have 2y y derivative equals minus 2x, so then you're left with y derivative equals minus 2x upon 2y, So then you're left with your y derivative equals minus x upon y, which is what we started out to prove. Okay, so we've shown there from that little bit of maths that is a solution, but the point of showing you that isn't really to go through the maths, it's just to look at it and say, well, what does it really mean graphically? So graphically you could draw that out. You can draw it like that. You know that the x squared plus y squared equals 1. Well, that's a circle. Okay, so what we'll do is we'll just draw a line up here that goes through that circle. Okay, so that's just a circle getting round there. So the circle will go all the way around, blah 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 blah. Okay, that's actually not too bad a circle. So if that's x and that's y there, then you know what it's saying is that if we were to take from our equation that we started off with, which is y derivative equals minus x, so we're saying y derivative equals minus x. Okay, then what we're saying is if we take y, okay, so what is y in this instance? We just draw one line through, then, well, y is that height there. Okay, so there's that height there, y. Now when we multiply y by something, we have to get minus x. Okay, so if I was to multiply y by, say, minus x upon y, and we try it and see whether that's going to work, well, these cancel out and you end up with minus x. Okay, so that means that this term here, y derivative, must equal minus x upon y. Okay, well, what's the gradient of this line? That line there is y. So what's the gradient of that line there? Well, the gradient of that line there, if I just pop it up there, is going to equal y upon x. Just rewrite that. It's going to equal y upon x. So that's the gradient of this line. So the gradient minus x upon y is going to be a line that runs perpendicular to that, okay? Because whenever you do parallel perpendicular gradients, you know that the gradient that's perpendicular is going to equal the value of the what's going to be m1, m2 going to equal minus 1. Okay, so the gradient of the line that's running perpendicular in this instance here, rather than being the value y upon x, it's going to equal minus x upon y. Okay, so that's just that. It's saying that line there. Okay, so what we're doing is we're taking the value of y, we're multiplying it by the gradient of the line there that's running perpendicular, and we're always getting a value of minus x. So if we were to pick a different point here, okay, there's a different point up there, then that would be that line there. Okay, and if we pick a point, say, down here, it would be that point there. Okay, so in this instance here, it means that we're always mapping out a circle, and this here is just giving us some kind of geometric inclination of description of what the differential equation means. Okay, and in these simple differential equations where there's only one independent variable, it means that you can always draw them out. If you've got enough imagination, you can draw them out and you can see that all of them have some kind of simple physical meaning in a simple two-dimensional way. Okay, so that's all there is for this video. I hope it's a starter for the differential equations. So through the rest of the videos, I'm just going to work through the differential equations that I find interesting and they're most well known. Okay, so thank you for listening and goodbye.